Hello everyone, I welcome you all. Now I am going to explain Fin apparatus in our heat transfer laboratory. The main aim of this experiment is to find out efficiency of the fin under natural and forced convection conditions. Come to the description of the apparatus. An aluminum fin of circular cross section having a length 195 mm and diameter 12 mm is fitted in a rectangular duct. The base of the fin is fixed to a heater plate for heating the fin. The duct is provided with a suction pan to control the airflow with the help of regulator. A multi-channel temperature indicator has been provided to monitor the different temperature points. An anemometer has been provided to measure the velocity of air. Power input to the heater regulator to vary the input power to the heater. This is the description of the apparatus. Let us go for the experimental procedure. First of all, I am conducting the experiment in natural flow condition. Before giving the power supply to the equipment, I am opening the windows provided at the top and bottom of the duct. I am giving the power supply to the equipment. Tripper on, switch on the console and switch on the heater. Give the some amount of the power to the heater. So observe the temperature indicator here. Here T1 indicates that means T1, T2, T3 indicates that temperature values at various positions of the fin, and T4 and T5 indicates that air inlet and outlet temperatures provided at the top and bottom of the duct. By using this temperature indicator, we can monitor the temperature values at various positions. Observe here the temperature values are varying with time, so the system is in unsteady state condition. Wait for some time till the system reaches to the steady state condition. After reaching the steady state condition, tabulate the values and go for the experimental calculation. These are the values recorded during the time of the experimentation. The values are recorded at each interval of 10 minutes. Observe the last two readings here. The variation is very low compared to these two readings. So we consider that these are the steady state readings. After reaching the steady state condition, we are consider these values and going to calculate the efficiency of the fin for these values. Before going to the calculation part, these parameters are already calculated. Surface temperature, we need the surface temperature, that's why I calculated the surface temperature, and this one is the ambient temperature, and length of the fin is 195 mm and diameter of the fin is 12 mm, and converts this into meters 0.195 meters and 0.012 meters, and perimeter of the fin is pi d, and cross sectional area of the fin is pi by 4 d square. These parameters will help at the time of the calculation. Come to the calculation part. The aim of this our experiment is to find out the efficiency of the fin. Efficiency of the fin is equal to the tan HML by ML. Here M equal to square root of HB by Ka. In this formula, H means heat transfer coefficient. We need to find out the heat transfer coefficient, and P means perimeter of the fin. Already calculated the perimeter of the fin. And K is the thermal conductivity of the fin. Thermal conductivity of fin is 205 watt per meter degree centigrade, and A is the cross sectional area of the fin. Cross sectional area already calculated here, and going to calculate the heat transfer coefficient here. From the heat transfer data book, the relation is considered for calculating the heat transfer coefficient value. HD by K equal to 0.85 into Gr dot Pr power 0.188. Here Gr means Grashopp's number and Pr means Prandtl number. For find out the Grashopp's number and Prandtl number, we need a properties of the air. So properties of the air values are considered at the film temperature. Film temperature is the average of surface temperature and the ambient temperature. So film temperature is 70 degree centigrade. So consider the properties of air at 70 degree centigrade. At 70 degree centigrade, Prandtl number equal to 0.694. Kinematic viscosity is 20.02 into 10 power minus 6 meter square per second. Dynamic viscosity is 20.59 into 10 power minus 6 Newton second per meter square. Thermal conductivity of the air 29.66 into 10 to the power of minus 3 watt per meter degree centigrade, and specific heat equal to 1.009 kilojoule per kg degree centigrade. So then find out the Grashopp's number by using these property values. This is the formula for the Grashopp's number. This Grashopp's number formula is again taken from the heat transfer data book. In this Grashopp's number, G indicates that acceleration due to gravity 9.81 into meter 9.81 meter per second square, and beta means the coefficient of thermal expansion, that equal to 1 by Tf. Here we need to substitute the film temperature value in terms of kelvins, and delta means difference between the surface temperature and the ambient temperature, and D is the diameter of the fin, and V square is the kinematic viscosity, already taken from the properties table in the heat transfer data book. Substitute all the values in the Grashopp's number. .81 into 2.91 into 10 to the power of minus 3 into surface temperature 112.6 minus 27.4 into diameter 0.012 whole cube divided by V square 20.02 into 10 to the power of minus 6 whole square. Let us calculate this value by using the calculator. One 103.00.27 is the Grashopp's number value. Prandtl number already taken from the properties table of the in the heat transfer data book. Substitute the Prandtl number and Grashopp's number in this equation. We will get the heat transfer coefficient value. That implies h into diameter 0.012 divided by thermal conductivity 29.66 into 10 to the power of minus 3 equal to 0.85 into 103.00.27 into Grashopp's number 0.694 whole power 0.188. Calculate. Let us calculate this value. I am simplifying again this formula. H equal to 0.85 103.00.27 into 0.694 power 0.188 into 29.66 into 10 to the power of minus 3 whole divided by 0.012. Let us calculate this value. Equal to 10.487 watt per meter square degree centigrade is the heat transfer coefficient H. Substitute the H value in this equation. We will get the M value here. M equal to square root of H into perimeter. P is 0.03768 divided by K, thermal conductivity. Here we need to substitute the thermal conductivity of fin into area, cross section area 1.1309 into 10 to the power of minus 4. Let's find out this value. 4.1285. Here we calculated the m value. So for substitute the value of m and L in this equation, we will get the efficiency of the fin here. Calculate the efficiency of the fin here. Tan H. Already calculated the m value, substitute here 4.1285. L value already given in the specifications, length of the fin 0.195 divided by ml 4.1285 into 0.195. Calculate this value. 0.80507. So efficiency of fin equal to 80.5 percentage. This is the efficiency of the fin. Conducted the experiment in natural flow conditions. Let us go for the experimental procedure of the forced flow condition. After conducting the experiment in a natural flow condition, turn off the heater and close the windows provided at the top and bottom of the duct. And observe the temperature values at the surface of the fin. The surface of the fin reaches to the room temperature. So after reaching the room temperature, let us start the experiment in forced flow condition. Observe here the temperature of the surface of the fin values reaches to the almost reached to the room temperature. So now I am conducting the experiment in forced flow conditions. Switch on the heater, switch on the regulator, fan regulator, and give the same amount of the heat input, whatever the heat input given in the earlier case. So by using the anemometer, measure the velocity of the air and wait for some time till the system reaches to the steady state condition. After reaching the steady state condition, again tabulate the values with velocity of the air. Wait for some time till the system reaches to the steady state condition. After reaching the steady state condition, tabulate the values and go for the experimental calculations. These are the values recorded during the time of the experimentation in forced flow convection. And observe that these two readings here, the variation is very low compared to these readings. So we consider that these are the steady state values. I am going to calculate the efficiency of the fin for these values. Before going to the calculation part, these parameters are calculated already. About these parameters discussed earlier. Come to the efficiency of the fin. This is the formula for the efficiency of fin, tan HML by ml. Here we know that m means square root of hp by ka, and ka is the thermal conductivity of the fin, 205 watt per meter degree centigrade. Here we need to calculate the h value for the purpose of calculating the m value. So we need to calculate the h value. First of all, find out the film temperature here. Film temperature is the average of surface temperature and the ambient temperature. So film temperature value is like this, 60.92 degrees centigrade. So take the properties of the air from the heat transfer data book at 60.92 degrees centigrade. These are the properties of the air at 60.92 degrees centigrade. So, let us first of all calculate the Reynolds number. Reynolds number is rho V d by mu. Here the rho means density of air, the density of air directly came from the properties table, and V means the velocity of air. Velocity of air is calculated during the time of the experimentation, and D means already given in the specifications. Diameter of the fin is 0.012 meters, and mu is the dynamic viscosity. It is comes from the properties table. So, substitute all the values here. 1.060 into velocity 1.9 meters into diameter 0.012 divided by dynamic viscosity 20.10 into 10 to the power of minus 6. Calculate this value by using the calculator. Double 167.22. Here the Reynolds number value is less than 4000. Here the Reynolds number value is less than 4000. So, the flow is laminar flow. In the laminar flow, consider the relation to find out the heat transfer coefficient in the data book. This relation is Nusselt number equal to 0.683 into RE power 0.446 into PR power 0.33. So, substitute all the values here. Reynolds number value just now we calculated, and Prandtl number value directly taken from the properties table. Substitute the values here. Nusselt number means we know the value, we know the form of Nusselt number. HD by K equal to 0.683 into 1167.22 whole power 0.446. Prandtl number 0.696 whole power 0.33. So, that implies H equal to 0.683 into 1167.22 whole power 446 into 0.696 whole power 0.33 into thermal conductivity K 0.02896 whole divided by diameter 0.012, that equal to H equal to 34.10 watt per meter square degree centigrade. So, let us calculate the value of M by using the H value and perimeter, thermal conductivity of the fin, and a cross sectional area. M equal to square root of HP by Ka, 34.10 into perimeter. Perimeter is 0.03768 by K 205. Cross sectional area is 1.1309 into 10 to the power of minus 3. Calculate this value. .44 is the value of M. So, substitute the value of M and length of the fin in this equation, we will get the efficiency of the fin. Substitute the values in the efficiency formula. Efficiency equal to tan h ml divided by ml. So efficiency equal to m value, just now calculated the m value. Length of the fin 0.195 meters divided by 7.44 into 0.195. Calculate this one by using the calculator. 0.6174. So efficiency of the fin in forced flow condition is 61.74%. Finally, I am concluding. I given the heat input to the system 80 watts and calculated the efficiency of the fin in forced flow condition and natural flow condition. In natural flow condition, the efficiency of the fin value is obtained at 80.68%, and forced flow condition, the efficiency of the fin value is obtained 61.74%. Thank you.